Welcome to Study Loop.
Part A of the given problem, treating the astronaut as a rigid body. We know that in the circular orbit about a black hole, so here's the black hole, the resultant force on each point of the body must be equal to Cp is equal to m times omega square r, where m is the mass of the and air is m, omega is the angular frequency, and r is the distance from a point of the black hole. Let us denote the distance between a black hole and air to be r plus minus a. The total force on each air must be compensated by the tension force that prevents deformation of the astronaut. So we can write minus m omega square r plus minus a is equal to minus g m times capital M times small m divided by r plus minus a whole square plus t. T is the tension force. Capital M is the mass of the black hole. For any point mass, which is m dash, of the astronaut at the distance r, we have minus m dash omega square r is equal to minus g capital M dash r square. From here omega square will be g capital M divided by r cube. Inserting this, let's call this equation A, into the equation 2 that we wrote. Let's call this as a 1. So we'll insert this equation A into 1. Then solve for a t. The t we get here is minus g capital M small m into 1 over r square plus minus a divided by r3 minus 1 divided by r plus minus a whole square. Since r is much greater than a, we use a Taylor series to approximate this equation that we wrote here. So 1 over r plus minus a whole square is equal to 1 divided by r square. 1 plus minus a divided by r whole square will be equal to, using a Taylor expansion, 1 over r square plus minus plus 2 into a divided by r square, r cube, plus or so on. We insert this approximation in our, let's say this is equation B. So inserting this approximation in equation B, the tension we get here is minus plus g m small m 3a divided by r cube. Using the information from the appendix of the book, appendix F, to find the sun's mass, and taking all the numerical values from the problem, we find the magnitude of the tension force in the radial direction to be approximately 2075 Newton. The magnitude of this force is quite large, and the astronaut is probably already torn apart. Part B of the problem, the center of the gravity is a point of the body about which the net torque vanishes. So center of mass is a point in space that can be computed by taking the weighted average of all points, which is r is equal to sum of mi I divided by sum of mi. In general, these 2 points, they don't coincide for a uniform gravitational field. These points coincide.